Right now, the space between the stars surrounding you sits at a temperature of negative 454 degrees Fahrenheit. That is negative 270 degrees Celsius. That is 2.7 Kelvin above absolute zero, which means the vast, silent ocean of space that separates every star from every other star, that fills the enormous distances between galaxies, that stretches across the majority of everything that exists, is hovering just barely above the coldest temperature the laws of physics will allow anything to reach. Just barely, 2.7 degrees above the end of warmth itself. And yet that number, as staggering as it sounds, is not the coldest place in the observable universe. There are places out there colder than empty space. There are nebulae clouds of gas drifting between stars that have managed to fall below even that threshold. Places where the universe has grown quieter than the void between galaxies. Places where matter has slowed so completely that the word cold no longer feels adequate. It feels like an understatement the way calling the ocean damp is an understatement. But here is what most people get wrong about space and cold. Space is not cold the way winter is cold. When you step outside on a January morning and the air bites at your face, what you are feeling is heat being pulled away from your body by moving air molecules. Cold in the human sense is an experience of loss. Heat leaving, warmth transferring from you into the environment around you. The cold does not come in, your warmth goes out, and the faster that transfer happens, the colder you feel. Space does not work that way. In the vacuum between stars, there is almost nothing to pull heat away from you. No air molecules pressing against your skin, no wind carrying your warmth into the distance. If you were somehow suspended in open space, you would not freeze quickly the way you might expect. You would actually overheat first, because the human body generates heat continuously, and in a vacuum there is almost no medium to carry that heat away. You would cook in your own warmth before the cold of space ever reached you. This is one of the first lessons the universe teaches when you look closely enough. Things are rarely what they appear to be from a distance. The cold that looks absolute is not simple. The silence that looks peaceful is not empty. The darkness that looks still is hiding motion beyond comprehension. And tonight, we are going to look closely. We are going to travel through the most extreme environments the observable universe contains. The coldest, the hottest, the densest, the most violent, the most utterly devastatingly empty. We are going to follow a path from the quietest corners of existence to the places where matter itself stops behaving like matter, where temperature climbs into ranges that make the surface of the sun look like a mild afternoon, where two objects smaller than a city can collide and briefly outshine entire galaxies. And at the end of that journey, we are going to return here, to this room, to this moment, to the extraordinarily unlikely fact of your existence in the middle of all of it. Because here is the truth that this journey keeps returning to. Every extreme place we will visit tonight, every temperature, every density, every act of cosmic violence, every void of impossible emptiness, all of it contributed in some way to the conditions that made you possible. The coldest clouds in space helped form stars. The hottest explosions forged the elements in your blood. The densest objects in existence seeded the universe with the raw materials of chemistry. The most violent events in cosmic history scattered those materials across space, so that billions of years later, gravity could gather them back together into something that breathes and wonders and listens in the dark. You are not separate from these extremes, you are downstream of them. If you enjoyed journeys that completely reshape how you see the universe and yourself within it, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow, and it means we can keep making these long, careful, quiet explorations together. Every subscription is a vote for more of this, and I am grateful for each one. Now make yourself comfortable, pull the blanket a little closer, let the day step back from you just a few paces. We are going to go somewhere vast tonight, and the best way to travel there is slowly and with your eyes half closed. Let's begin. To understand why the universe contains extremes at all, it helps to first understand what the universe is made of and what it is doing. Because the universe is not a static collection of objects sitting quietly in darkness. It is a system, a vast, ancient, continuously evolving system of matter and energy and forces interacting across distances so enormous that every unit of measurement we invented for human purposes, the mile, the kilometer, the light year, eventually runs out of usefulness, and we are forced to invent new ones. And systems, by their nature, create gradients, differences, places where one quantity is higher than elsewhere and places where it is lower. When you heat one end of a metal rod and cool the other, a gradient forms. Energy flows from the hot end toward the cold end. The system tries to balance itself. Nature everywhere tends toward equilibrium, toward the evening out of differences, toward the patient dissolution of gradients into uniformity. The universe has been doing exactly this since the moment it began. But the universe began in a state of such extreme imbalance, such staggering asymmetry between energy-dense regions and emptier ones, that even after nearly 14 billion years of trying to even itself out, gradients still exist everywhere. Stars are hotter than the space around them, black holes are denser than the gas they consume, certain clouds are colder than the void between galaxies. The universe has been working toward balance for almost incomprehensible spans of time, and it is nowhere close to finished. This is why extreme places exist. Not because the universe is dramatic by intention, but because balance is hard to achieve at scale, and the scale here is everything. Now, when we say extreme, we mean something precise. We mean environments where the ordinary rules of matter and energy that govern daily life on Earth no longer apply in their familiar forms, where atoms cannot hold together in the usual way, where the distinction between a solid and a liquid becomes meaningless, where radiation so intense fills every cubic centimeter that human biology would last microseconds, where gravity bends not just the paths of objects, but the fabric of time itself. These are not metaphors. These are measured, documented, observed realities. And the first of them, the one we will enter tonight through the quietest possible door, is cold. Not the cold of a winter morning, not the cold of a freezer or a mountain summit, or even the cold of the Antarctic interior, where temperatures can fall to negative 128 degrees Fahrenheit, and survival becomes a matter of minutes rather than hours. The cold we are moving toward is something else entirely. To understand it, we need to understand what temperature actually is. Not the number on a thermometer, but the physical reality that number represents. Temperature is a measure of motion. Specifically, it is a measure of the average kinetic energy of the particles in a substance. Hot things are hot because their atoms and molecules are moving, rapidly vibrating, bouncing, colliding with one another in constant chaotic motion. Cold things are cold because that motion has slowed. When you cool something down, you are removing energy from it. You are slowing its particles. And absolute 00 Kelvin, negative 459.67 degrees Fahrenheit, is the temperature at which that motion would stop entirely, the point at which all thermal motion ceases, the floor beneath which temperature cannot fall because there is no more motion left to remove. It is theoretically unreachable. Quantum mechanics ensures that even at temperatures approaching absolute zero, particles retain a small residual energy called zero-point energy. They never quite stop, but objects can approach that limit with extraordinary precision, and in certain corners of the universe they do. The background temperature of space, that 2.7 Kelvin we mentioned at the beginning, is not arbitrary. It is the temperature of the cosmic microwave background radiation, the ancient afterglow of the Big Bang itself. When the universe was approximately 380,000 years old, it had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was a hot, dense plasma through which light could not travel freely. Photons scattered constantly off charged particles like sunlight scattering through fog. Then, in an event cosmologists call recombination, the fog cleared. Light was suddenly free to travel, and it has been traveling ever since, stretching as the universe expands, cooling as it stretches until today. It fills all of space as a faint microwave glow at 2.7 Kelvin. That glow is the oldest light in the universe. It surrounds you right now in every direction. You cannot see it with your eyes. Your eyes are not built for microwaves, but it is there, bathing you from all sides. A whisper from 14 billion years ago, the last remnant of an era when everything was fire. And its temperature, 2.7, Kelvin sets the floor for most of the universe. To be colder than that, you would need to be radiating heat faster than the cosmic microwave background is delivering it to you. You would need to be actively losing warmth to become colder than space itself. Some clouds of gas between the stars have managed to do exactly that. They are called dark nebulae, dense molecular clouds, vast regions of gas and dust that have not yet collapsed into stars. These clouds are cold by any standard. Their interiors can fall to temperatures of 10 Kelvin, 20 Kelvin. But the most extreme of them, the one that has earned a name and a permanent place in the catalogue of cosmic curiosities, is a cloud called the Boomerang Nebula. It sits approximately 5,000,000 light-years from Earth in the constellation Centaurus. To look at it through a telescope, it appears as a pale, roughly symmetric smear of light, unremarkable in shape, easily overlooked in the catalogue of more dramatic objects. But its appearance is deceptive. Its temperature is not. The Boomerang Nebula sits at approximately 1 Kelvin, 1 degree above absolute zero, colder than the cosmic microwave background, colder than the space between galaxies. The coldest natural environment ever measured in the observable universe. How does something get colder than space itself? The Boomerang Nebula is the remnant of a dying star, a star similar in mass to our Sun that has begun shedding its outer layers. Gas is streaming outward from the dying star at roughly 100 miles per second, or about 160 kilometers per second. As this gas expands rapidly into the surrounding space, it cools through a process called adiabatic expansion. The same principle that makes the air from an aerosol can feel cold when you spray it. Rapidly expanding gas loses thermal energy. The faster the expansion, the more dramatic the cooling. In the Boomerang Nebula, the expansion is fast enough and the outflow dense enough that the gas cools below the temperature of the surrounding cosmic microwave background. It radiates away even the faint warmth that space itself provides, and so it falls below the universal floor. It becomes, in a very precise and measured sense, the coldest place we know of, 1 Kelvin, 458 degrees below 0 Fahrenheit, a temperature at which ordinary matter enters states with no everyday analogue, a temperature at which the distinction between physics and philosophy begins very gently to blur. Now hold that image for a moment. A cloud of gas 5,000 light-years away slowly streaming outward from a dying star at a temperature 1 degree above the coldest anything can be. Picture it not as a dramatic scene but as an almost unbearable quietness. The particles in that cloud are barely moving. The energy has been stripped away so completely that what remains is nearly the physical definition of stillness. And yet that cloud will not stay cold forever. Eventually, gravity will do what gravity always does. It will pull the material inward. The cloud will compress. Compression creates heat. The temperature will rise. And if enough mass accumulates in the right conditions, that cold, quiet, nearly motionless gas will collapse into a new star, a furnace of nuclear fire where hydrogen fuses into helium at millions of degrees, a place as hot as anything in the galaxy, born from a place as cold as anything in the universe. Cold gives birth to heat. Stillness gives birth to fire. This transformation is not a metaphor. It is thermodynamics. It is gravity. It is the universe doing what it has been doing for 14 billion years, taking gradients and pushing them toward new gradients, taking extremes and producing new extremes, never quite reaching the balance it is always working toward. And that cycle, from cold cloud to hot star to exploded star to new cold cloud, is one of the oldest and most important recycling systems in existence. The carbon in your body was forged in the cores of stars that no longer exist. The iron in your blood was scattered by air. Resuperhang, supernova explosions billions of years before the solar system formed. You are in the most literal chemical sense a product of these cycles. Your atoms have been through temperatures ranging from the nearly absolute cold of interstellar clouds to the millions of degrees at the center of stellar cores. You have been, in a sense, everywhere. You just weren't assembled yet. Now, as the Boomerang Nebula drifts in its quiet, cold 5,000 light-years away, as its particles barely vibrate at 1 Kelvin above, absolute zero, as the ancient starlight of the cosmic microwave background tries and fails to warm to it from all directions, There is a patience to it that is almost calming. Nothing is rushing, nothing is burning, nothing is colliding or exploding or tearing apart, just gas moving outwards, slowing cooling, approaching the lower limit of thermal existence with a kind of inevitable grace. But the universe will not let it stay that way. It never does. Because the universe is not in the business of permanent stillness. It is in the business of transformation, and transformation requires both extremes. The coldest places and the hottest places are not opposites in the way we often think. They are partners in the same cycle. Cold collapses into heat, heat explodes into cold. The pendulum swings, and the arc of that swing spans temperatures so vast that the human mind encountering them honestly tends to simply go quiet for a moment. That is not a failure of imagination. That is imagination working correctly. Some things are so large, so far outside the range of lived experience, that the appropriate response is not to pretend you have grasped them fully. The appropriate response is to sit with the number, to let it rest in your mind, without demanding that it feel familiar, to allow the strangeness of it to do its gentle work of expanding your sense of what is real. 2.7 Kelvin is the temperature of space. 1 Kelvin is colder than space. And somewhere in the darkness between the stars, a cloud of gas from a dying sun drifts at that temperature 1 degree above the end of warmth, waiting for gravity to remind it what fire feels like. There is a number that physicists carry with them, the way other people carry certain memories, not because it is beautiful in the conventional sense, though there is a kind of beauty in it, not because it is useful in daily life, though it underpins entire fields of science. They carry it because it represents a limit. A hard, absolute, non-negotiable boundary built into the structure of reality itself. A place where the physical universe draws a line and says no further. That number is 0. 0 Kelvin, negative 459.67 degrees Fahrenheit, negative 273.15 degrees Celsius, absolute zero. In the entire history of the universe, across all 14 billion years of stars forming and dying, of gas collapsing and exploding, of matter cycling through every state and condition, physics allows nothing has ever reached that a temperature. Not the Boomerang Nebula at 1 Kelvin, not the most carefully engineered laboratory experiments on Earth, where physicists have cooled small samples of matter to within billionths of a degree of absolute zero using lasers and magnetic fields and techniques that would have seemed like science fiction a century ago. Nothing has touched that floor, and the reason is subtle and strange and worth sitting with for a moment. Quantum mechanics, the set of rules that governs behavior at the scale of atoms and smaller, does not permit complete stillness. Even at temperatures approaching absolute zero, particles retain what is called zero-point energy, a residual irreducible vibration that cannot be removed no matter how much heat you extract. It is not a failure of engineering. It is not a limitation we might overcome with better technology. It is written into the mathematical structure of reality. Particles are not simply small objects sitting still or moving. They are quantum entities with inherent uncertainty in their position and momentum simultaneously. That uncertainty manifests as motion that can never fully cease. So, absolute zero is a limit that the universe approaches but never reaches, like a line drawn on a map that you can walk toward forever without arriving. The closer you get, the harder it becomes to go further. The universe seems to protect its own floor, and yet things can get extraordinarily close. In laboratories on Earth, physicists working with ultra-cold atomic gases have cooled matter to temperatures measured in nanokelvin, billionths of a degree above absolute zero. At those temperatures, matter enters states with no analog in ordinary experience. Bose-Einstein condensates form collections of atoms that begin to behave as a single quantum entity, losing their individual identities and merging into a collective state that is neither solid, nor liquid, nor gas, but something that existed only in theory until 1995, when Eric Cornell and Carl Wieman at the University of Colorado created the first one in a laboratory using a cloud of rubidium atoms cooled to 170 nanokelvin. They received the Nobel Prize in Physics 6 years later. What they had created was, for a brief moment, the coldest thing in the known universe, colder than the Boomerang Nebula, colder than the void between galaxies. colder than anything nature had managed to produce in 14 billion years of trying. A small cloud of atoms in a laboratory in Colorado. That is one of those facts that rewards careful attention. The coldest thing in the universe at the moment of its creation was sitting in a building in the American West, made by human hands, held in place by laser beams and magnetic fields, lasting only fractions of a second before warming back into the ordinary thermal world. Scale is genuinely unreliable as a guide to significance. But we are here tonight to travel through the universe, not a laboratory. And the universe has its own cold places, its own quiet extremes, spread across distances that make the Boomerang Nebula feel like a neighbor. Beyond the familiar scale of individual nebulae and dying stars, there are structures in the universe so vast and so cold that they require an entirely different frame of reference to comprehend. These are the cosmic filaments and voids, the large-scale architecture of the universe itself, the skeleton on which galaxies are arranged like dew on a spider's web. If you could pull back far enough from the Milky Way, far enough that individual stars became invisible, far enough that even galaxies were reduced to faint smudges, you would begin to see the universe's largest structures emerge. Long filaments of matter, hundreds of millions of light years in length, connecting clusters of galaxies like threads in a vast three-dimensional web. Between those filaments, immense empty regions called cosmic voids, spaces so devoid of matter that entire galaxy clusters could drift through them without finding a neighbor for hundreds of millions of light years in any direction. The temperature inside a cosmic void is close to the cosmic microwave background temperature, 2.7 Kelvin. Not quite as cold as the Boomerang Nebula's extraordinary 1 Kelvin, but cold in a way that is harder to comprehend because of the scale. Not one cloud, not one nebula, but a region of space hundreds of millions of light years across, containing almost nothing, maintained at a temperature barely above absolute zero, existing in a silence so complete that the word silence becomes inadequate. We will return to those voids later in our journey tonight because they represent a different kind of extreme entirely. Not the cold of compression and expansion, not the cold of stellar remnants and dying stars, but the cold of absence. The cold of a universe that has spread itself so thin in certain regions that matter has simply given up the conversation. For now, let us stay with the cold that creates. Because the most important thing about cold, cosmically speaking, is not what it destroys or what it ends. It is what it makes possible. A molecular cloud is in many ways the most important object in the universe. Not the most dramatic, not the most violent, not the most luminous or the most massive or the most energetically impressive, but the most important in the sense that without it, nothing else we will discuss tonight would exist. No stars, no planets, no heavy elements, no biology, no one to notice any of it. A molecular cloud is a region of interstellar space where gas and dust have accumulated to densities high enough for molecules to form. Not just atoms, but actual molecules. Hydrogen molecules, carbon monoxide, water ice, complex organic compounds, all drifting in the cold dark between the stars at temperatures ranging from roughly 10 to 30 Kelvin. Cold enough that chemistry can happen without the molecules being immediately torn apart by radiation. Cold enough that the thermal energy pushing particles apart is weak enough for gravity to eventually win. The Milky Way contains several thousand of these clouds. The largest, called giant molecular clouds, can contain millions of times the mass of our sun stretched across hundreds of light years. The Orion Molecular Cloud, which lies behind the visible Orion Nebula, roughly 1300 light-years from Earth, is one of the closest and most studied. It contains enough mass to form tens of thousands of stars. Some of that star formation is happening right now as you listen, gas collapsing in the dark of that cloud heating as it falls inward, approaching the threshold where fusion ignites and a new star is born. Every star in the night sky began this way, in the cold, in the dark, in the quiet patience of a molecular cloud slowly yielding to gravity. And here is the thing about that process that tends to get lost in more dramatic descriptions of stellar birth. The collapse is not instant. It is not explosive. It does not happen the way a bomb goes off or a dam breaks. It happens with geological slowness over millions of years, driven by the most patient force in the universe. Gravity does not hurry. A region of a molecular cloud might become slightly denser than its surroundings due to a passing shock wave from a distant supernova or a collision with another cloud, or simply the slow statistical drift of particles. That slight density increase means slightly stronger gravity. Slightly stronger gravity pulls in slightly more material. More material means more gravity. The process feeds itself in a loop that takes millions of years to complete, but that almost always ends the same way, with fire, with a star. Now, consider the temperature journey that material takes. It begins in the cloud at perhaps 10 or 15 Kelvin, barely above absolute zero, barely vibrating, barely interacting with anything around it. It falls inward under gravity, compressing, heating. The center of the forming star, called a protostar, reaches temperatures of a few thousand Kelvin, then tens of thousands. Then, when the core is dense enough and hot enough, nuclear fusion ignites, and the temperature at the center crosses 10 million Kelvin. From 10 Kelvin to 10 million Kelvin, a journey of 7 orders of magnitude in temperature, driven by nothing more than gravity pulling gas downward into itself. That is the cold doing its work, providing the raw material, the compressed, quiet, nearly motionless reservoir of matter that gravity needs to build something extraordinary. Without the cold, the gas would be too hot, too energetic, too diffuse for gravity to gather. The universe needs cold regions to make hot stars. Extremes require each other. Now, let us go somewhere specific within one of these clouds. Let us go to a place called a prestellar core. This is the densest, coldest region inside a molecular cloud, the place where collapse is most advanced, the place closest to the threshold of stellar ignition. These cores are typically a few tenths of a light year across, containing perhaps a solar mass or two of gas and dust, at temperatures as low as 6 or 7 Kelvin, 6 Kelvin, 6 degrees above absolute zero. Inside that core, something is happening that is easy to miss if you are looking for drama. Very slowly, imperceptibly from any human timescale, the center is pulling itself together. Molecules are drifting inward, dust grains are aggregating. The density at the very center. There is a moment theoretically predictable but practically impossible to observe directly when the center of that core crosses a threshold, when the infall of material becomes rapid enough and the central density high enough that the region becomes opaque to its own radiation. Heat can no longer escape easily. It builds, the temperature climbs, and from that moment, the process accelerates. The protostar is forming. It will take hundreds of thousands more years before that protostar becomes a true star, fusing hydrogen in its core and pushing back against the gravity that created it. Hundreds of thousands of years of slow, dark, cold transformation before the first light. But the outcome from the moment of that threshold crossing is essentially determined. Gravity has committed. The star will form. That journey from cold molecular cloud to burning star is, in a quiet way, one of the most violent transformations in the universe. Not violent in the way we usually mean the word, not explosive or sudden, but violent in the sense of total transformation of a system passing through a one-way door from which there is no return. The gas that enters a protostellar collapse does not come back out as a cold molecular cloud. It becomes something entirely different, something that will burn for millions or billions of years, something that will eventually die in its own transformation, scattering its material back into the galaxy to form new cold clouds, new protostars, new planets, new chemistry. The cycle does not end, it only transforms. There is one more aspect of cold that deserves attention before we begin our ascent toward the hottest places in the universe, and it is perhaps the most surprising. Cold is creative not just because it provides the raw material for star formation. Cold is creative because it allows chemistry to happen. In the warm environments near stars, molecules tend to be torn apart by radiation and energetic collisions. The atoms exist, but they cannot combine into complex structures. They are kept simple by heat. But in the cold reaches of molecular clouds away from stellar radiation, at temperatures of 10 or 15, Kelvin chemistry can proceed slowly and without interruption. Atoms combine into molecules. Simple molecules combine into more complex ones. On the surfaces of dust grains, where molecules can stick and react without immediately being disrupted, some of the most complex chemistry in the universe occurs in some of the coldest places in the universe. Astronomers have detected over 200 different molecular species in interstellar clouds: water, carbon monoxide, ammonia, methanol, formaldehyde, complex organic molecules containing carbon, hydrogen, oxygen, and nitrogen, arranged in structures that begin to resemble the building blocks of biology. Some meteorites that have fallen to Earth contain organic molecules whose isotopic signatures suggest they formed in the cold environment of interstellar space before the solar system existed, carried here across billions of years inside rocky messengers from the early solar system. The chemistry of life may have begun not in a warm pond on a young Earth, but in the cold, dark between the stars, not in heat but in cold, not in the presence of energy, but in its near absence. That possibility has not been proven, but it has not been ruled out, and it is worth sitting with because it inverts a story we often tell ourselves about life and warmth. We associate living things with heat, with activity, with the fast-moving chemistry of warm cells in warm bodies, and that is true of life as we experience it today. But the origins, the first tentative steps toward the molecular complexity that eventually became biology, may have happened in a place as cold as anything this side of absolute zero. You may be in some ancient chemical sense a child of the cold. Let us take stock of where we are before we begin to climb. We have visited the coldest natural place in the observable universe, the Boomerang Nebula at 1 Kelvin, colder than the cosmic microwave background, colder than the void between galaxies, a cloud of gas exhaled by a dying star, cooling as it expands, approaching but never reaching the absolute limit of thermal existence. We have understood what that limit is and why it cannot be crossed absolute zero, the temperature at which all thermal motion ceases, protected from ever being reached by the quantum mechanical certainty that particles can never be entirely still. We have visited molecular clouds, the vast cold nurseries of the galaxy where temperatures of 10 to 30 Kelvin provide the conditions that gravity needs to build stars, where chemistry proceeds in the dark, where organic molecules form on the surfaces of dust grains, where the material of future planets and future life drifts in patient cold waiting. And we have followed a single parcel of gas from the deepest cold of a prestellar core, through the slow, inevitable collapse of gravity, toward the threshold of fusion, where cold becomes fire in a transformation that takes millions of years and leaves nothing unchanged. Now we begin to climb, because the universe does not only contain the coldest places, it contains places so hot that the word hot becomes a placeholder for a reality that ordinary language was never designed to describe. Places where temperatures climb not into the thousands of Kelvin, not into the millions, but into the billions, into ranges where matter, as we understand, it ceases to exist, and something stranger, something more fundamental, something that has not been seen in the universe since its earliest moments, takes its place. We are heading toward the hottest places in the observable universe, and the journey there will pass through a star. The surface of the Sun is approximately 5778 Kelvin. That number by any human standard is incomprehensible as a lived experience. The hottest temperature ever recorded on Earth's surface was 56.7 degrees Celsius in Death Valley, California in 1913, a temperature at which survival without shelter becomes a matter of hours. The surface of the Sun is roughly 340 times hotter than that, a place where iron does not merely melt but boils, where rock exists only as plasma, where the concept of a solid object becomes physically meaningless because no arrangement of atoms can maintain structural integrity against the thermal energy tearing it apart. And yet, the surface of the Sun is not particularly hot by cosmic standards. It is not even the hottest part of the Sun. It is in the hierarchy of temperatures the universe contains a relatively modest starting point, a first rung on a ladder that climbs so high it eventually disappears into conditions where our best physical theories begin to strain at their own foundations. Let us climb that ladder carefully. The Sun's surface, at 5778 Kelvin, is the layer called the photosphere. This is the visible disk we see from Earth, the source of the light that crosses 93 million miles of space and arrives at your skin as warmth. Below the photosphere, the sun becomes opaque. Light generated in the core cannot travel directly outward. It bounces, scatters, is absorbed and re-emitted countless times in a random walk that takes on average somewhere between 100,000 and 1700,000 years to complete. A photon created by nuclear fusion in the solar core today will not reach the surface for tens of thousands of years. Then it crosses 93 million miles of vacuum in 8 minutes and 20 seconds. 8 minutes to cross space, tens of thousands of years to cross the sun. That contrast says something important about the density of stellar interiors. They are not empty. They are not even loosely packed. They are so dense that light itself is trapped, redirected, slowed to a crawl by the sheer number of particles it must navigate. A photon moving at the speed of light through ordinary space can cross the diameter of our solar system in about 11 hours. That same photon inside the sun might travel only a few centimeters before being absorbed and re-emitted in a random new direction. The sun is not a burning ball of gas in the way a campfire burns. It is something stranger, a contained self-sustaining nuclear furnace so dense at its center that the laws governing energy transport read very differently than they do in open space. Now let us descend. As we move from the photosphere inward through the sun's interior, temperature rises. The convection zone, the outer third of the sun, where heat is transported by the actual movement of hot plasma rising and cool plasma sinking, much like a pot of boiling water, ranges from the photosphere temperature at its outer boundary, roughly 2 million Kelvin at its base. 2 million Kelvin. At that temperature, atoms are fully ionized. There are no electrons orbiting nuclei in neat quantum shells. There are only bare nuclei and free electrons. A plasma moving at speeds measured in hundreds of kilometers per second, colliding, constantly carrying energy outward through the sheer violence of their motion. Below the convection zone lies the radiative zone, where energy moves not by bulk fluid motion but by radiation photon, by painful photon absorbed and re-emitted in that slow, random walk toward the surface. Temperatures in this region range from 2 million Kelvin at the outer boundary to approximately 7 million Kelvin approaching the core. And then the core? The solar core occupies roughly the innermost 20 to 25% of the sun's radius. It contains approximately half the sun's mass compressed into that volume. The temperature at the center of the solar core is approximately 15 million Kelvin. 15 million Kelvin. If you took the surface temperature of the sun, already hot enough to boil iron, and multiplied it by 2600, you would approach the temperature at the center of this ordinary, middle-aged, unremarkable star. A star that astronomers classify as a yellow dwarf, a designation that carries no superlatives, no extremes, no drama. An average star, a common star, one of roughly 200 billion in the Milky Way alone. At 15 million Kelvin, nuclear fusion becomes possible. Protons, the nuclei of hydrogen atoms, are moving fast enough, and the density is high enough that they can overcome their natural electromagnetic repulsion and fuse together. 4 hydrogen nuclei combine through a chain of reactions into one helium nucleus. The helium nucleus has slightly less mass than the 4 protons that created it. That missing mass, a small fraction of the original, is converted directly into energy, according to the equation that changed human history. Every second, the sun converts approximately 600 million tons of hydrogen into approximately 596 million tons of helium. The missing 4 million tons becomes energy, becomes light, becomes warmth, becomes the photons that will spend tens of thousands of years bouncing toward the surface before crossing space in 8 minutes and arriving here on Earth, sustaining every living thing on the planet. 4 million tons per second, converted entirely into energy for the past 4.5 billion years, with approximately 5 billion years remaining. That is the engine running silently beneath the light you have known your entire life. But the sun, remarkable as it is not the upper limit, not even close. To find hotter places, we need to find more violent events. And the most violent stellar event we know of, the one that briefly concentrates more energy into a smaller space than almost anything else in the universe, is the collapse of a massive star's core in the first moments of supernova. We visited supernovae in the context of violence earlier. Now let us visit them in the context of temperature, because the temperature reached during core collapse is not merely impressive, it is transformative in ways that shape the chemistry of everything you have ever touched. In the final moments before a massive star's core collapses, when the iron core has grown to approximately 1.4 times the mass of our Sun and can no longer support itself against gravity, the collapse happens with breathtaking speed. The core, which had been roughly the size of Earth, collapses to a sphere roughly 30 kilometers across in less than a second. The density increases by a factor of roughly 1 trillion, and the temperature at the center of that collapsing core climbs to approximately 100 billion Kelvin. 100 billion Kelvin. Let us hold that number beside the others we have gathered. The surface of the Sun, 5778 Kelvin. The core of the Sun, 15 million Kelvin. The collapsing core of a massive star, 100 billion Kelvin. The jump from the solar core to the supernova core is not a factor of 2 or 10 or 100. It is a factor of nearly 7,000. 7,000 times hotter than the center of the Sun. A temperature so extreme that the nuclear reactions occurring there are not the careful, patient fusion of hydrogen into helium that powers stars throughout their long lives. They are something more chaotic, more energetic, more destructive, and more creative simultaneously. At 100 billion Kelvin, atomic nuclei are photodisintegrated. The gamma rays filling that environment are so energetic that they smash apart the iron nuclei that took millions of years of stellar evolution to build, breaking them back down into protons and neutrons. Entire elements are unmade in fractions of a second. The work of a star's lifetime is undone in a moment. But that is only part of the story, because the outer layers of the star falling inward and then rebounding off the suddenly stiffened core in the shock wave that will eventually become the supernova explosion itself are also heated to extreme temperatures. Not as extreme as the core, but extreme enough for a different and critical process to occur. In the turbulent energetic environment of the shockwave, and the outer core neutrons are captured by atomic nuclei in rapid succession. This process, called the R process, the rapid neutron capture process, builds heavy elements, elements heavier than iron, elements that cannot be made by ordinary stellar fusion. Gold, platinum, uranium, lead, silver, every piece of gold that has ever been worn as jewelry, traded as currency, used in electronics, or stored in a vault was created in the final moments of a dying star, in temperatures exceeding tens of billions of Kelvin, in an environment so violent that the very nuclei of atoms were being torn apart and rebuilt on timescales of fractions of a second. The ring on a finger, the circuitry in a phone, the gold standard of ancient economies, all of it forged in stellar catastrophe at temperatures that would vaporize any concept of solid matter 1 billion times over. That is not a metaphor. That is nuclear physics. Now let us keep climbing, because supernovae, extraordinary as they are not the hottest environments the universe currently contains. For that we need to look to the places where matter cabatta, specifically the accretion disks of the most actively feeding black holes in the universe. We discussed quasars in the context of their luminosity. Now let us revisit them through the lens of temperature. The accretion disk surrounding an actively feeding supermassive black hole is a structure of layered extremes. Its outer regions, where gas is just beginning to spiral inward, may be at temperatures of tens of thousands of Kelvin. Hot certainly by any ordinary standard, but relatively modest compared with what lies closer to the center. As material spirals inward and the orbital velocity increases and compression intensifies and magnetic fields twist and snap and reconnect, temperatures climb. The inner regions of a quasar accretion disk, close to the innermost stable circular orbit around the black hole, can reach temperatures of millions of Kelvin. The X-ray emitting corona above the disk, a poorly understood region of extremely hot magnetized plasma that hovers above the disk and produces some of the most energetic radiation we detect from these systems, can reach temperatures of billions of Kelvin. Billions of Kelvin. In a structure larger than our entire solar system, sustained not for fractions of a second, like a supernova core, but for millions of years, as long as gas continues to fall inward. Not a brief flash of extreme temperature, but a sustained furnace operating at conditions that have no parallel in the stable universe of ordinary stars. And yet, even the multi-billion Kelvin corona of a feeding quasar is not the upper limit, because we have not yet gone back to the beginning. To find the hottest temperatures in the history of the universe, we do not look outward across space, we look backward across time. In the first moments after the Big Bang, the universe was not the cool, structured, galaxy-filled expanse we inhabit today. It was a state of incomprehensible density and temperature, a condition so far removed from ordinary experience that physicists use different language to describe it, language borrowed from quantum field theory and general relativity, thermodynamics all at once, because no single framework is sufficient. At 1 second after the Big Bang, the temperature of the universe was approximately 10 billion Kelvin. At that temperature, the universe was filled with a hot plasma of protons, neutrons, electrons, photons, and neutrinos, all interacting furiously, all in thermal equilibrium, all part of a single seething environment where the distinction between matter and energy was far less clear than it is today. At 1/100th of a second after the Big Bang, the temperature was approximately 100 billion Kelvin. The same temperature reached briefly at the center of a collapsing supernova core. But where the supernova reaches that temperature, in a region the size of a city, for a fraction of a second, the entire observable universe existed at that temperature simultaneously. Not a point, not a region, everything. Go back further. At 1 microsecond after the Big Bang, the temperature was approximately 1 trillion Kelvin. At that temperature, protons and neutrons could not exist as stable particles. Matter existed in a state called quark-gluon plasma, a hot, dense soup of quarks and gluons, the fundamental constituents of protons and neutrons moving freely unconfined by the strong nuclear force that normally binds them together. A state of matter that does not exist anywhere in the natural universe today, except in the fleeting moments created by collisions in particle accelerators, like the Large Hadron Collider at CERN, where physicists have briefly recreated temperatures approaching a few trillion Kelvin in tiny volumes, lasting fractions of a second. A trillion Kelvin in a machine built by human beings, a temperature that existed naturally in the entire universe when it was 1 microsecond old. That comparison is worth pausing on. The most powerful particle accelerator humanity has ever built can recreate in a space smaller than an atomic nucleus for a duration shorter than any clock, can measure the conditions that filled the entire observable universe when it was a millionth of a second old. We are not recreating something foreign, we are recreating something ancestral, something the universe passed through on its way to becoming what it is now. We are in those experiments briefly visiting our own origin. Go back further still and the temperature climbs into ranges where our physical theories themselves begin to break down. At the Planck time, approximately 10 to the negative 43 seconds after the Big Bang, the temperature was approximately 10 to the 32 Kelvin. 100 million trillion Kelvin. At that temperature and density, quantum gravitational effects become important, and we do not yet have a complete theory of quantum gravity. Our map of physics has an edge, and that edge is approximately 10 to the negative 43 seconds into the universe's history. Before that moment, or more precisely at conditions more extreme than those at that moment, we do not know what happened, not because we have not looked carefully enough, not because the data is insufficient, but because the theoretical framework we would need to describe such conditions does not yet fully exist. This is one of the most honest admissions in all of science. We have traced the universe backward in time, climbed the temperature ladder from the cold of molecular clouds, through stellar cores, through supernova, through quasar accretion disks, through the first seconds of cosmic history, and we have arrived at a wall, a place where our best tools, our most carefully tested theories, our most precisely calibrated mathematics reach their limit. Beyond that wall, we do not know, and that not knowing is not a failure. It is an invitation. It is the frontier that every physicist who has ever felt the pull of fundamental questions carries with them. The place where the next great understanding waits patient and dark for someone to find the right question to ask. Now, let us stand back for a moment and look at the full range of temperatures we have traversed tonight so far. From 1 Kelvin in the Boomerang Nebula, a single degree above the coldest, anything can be to 10 to the 32 Kelvin at the Planck epoch, a temperature so extreme that our theories of physics reach their boundary. The range between those two extremes spans 32 orders of magnitude, 32 powers of 10. To put that in some kind of perspective, the difference in size between a proton and the observable universe spans roughly 41 orders of magnitude. The temperature range of the universe is almost as vast as the size range of the universe. Everything we experience in daily life, the warmth of a fire, the cold of a winter morning, the heat of a forge, the chill of a mountain lake, fits into a tiny sliver of that range. A sliver so narrow that on a graph spanning the full temperature range of the universe, human experience would be invisible, a line thinner than a pencil mark, a whisper between extremes. And yet within that whisper, chemistry is possible, biology is possible, consciousness is possible. The full complexity of everything human beings have ever built, felt, thought, created, mourned, celebrated, whispered to the people they love in the dark. All of it occurs within a range of temperatures so narrow relative to what the universe contains that its existence feels almost improbable. Almost, because the universe is roughly 13.8 billion years old, and for most of that time the temperatures required for life as we know it have existed in certain places, not everywhere, not even in most places, but in enough places on enough worlds, orbiting enough stable stars that chemistry had time to become biology, and biology had time to become whatever it is that lies awake at night, thinking about the temperature of the Boomerang Nebula. The cold made the stars made the elements made the planets made the oceans made the chemistry made you. That chain is not a metaphor. It is a sequence of physical processes, each dependent on the one before, each occurring over timescales that dwarf human history, each building on the work of extremes that exist nowhere near your present comfort. You are the product of a temperature range spanning 32 orders of magnitude. You live in a thin band near the middle of it, and within that band you are warm enough for chemistry and cool enough for structure, warm enough for thought and cool enough for sleep. That is not nothing. That is in the full context of the universe's thermal history almost everything. Now we have climbed from cold to hot, from the nearly absolute stillness of a cloud of gas exhaled by a dying star to the unimaginable furnace of the first moments of time. We have passed through stellar cores and supernova shocks and quasar accretion disks and the seething plasma of the early universe. We have arrived at the edge of what our physics can describe, but temperature is not the only measure of extremity. Heat is not the only form that violence takes. Because there are places in the universe where matter is compressed not to extreme temperatures, but to extreme densities. Places where the question is not how hot something is, but how much is packed into how small a space. Places where the pressure is so intense that ordinary matter ceases to exist in any form we would recognize, and something new, something that exists at no other scale in the observable universe takes its place. We are heading toward the densest places in existence, toward objects that contain more mass than our sun packed into a sphere you could walk across in a morning, toward matter under pressures so extreme that atomic structure dissolves and something stranger emerges. We are heading toward neutron stars, and what waits there is worth the journey. Take a teaspoon, an ordinary kitchen teaspoon, the kind used to stir coffee or measure vanilla extract or scrape the last traces of something good from a small jar. Hold it in your hand for a moment and consider its volume, perhaps 5 milliliters, perhaps a little less. A small, inconsequential amount of space easily overlooked, the kind of measurement that appears in recipes without drama. Now, fill that teaspoon with neutron star material. It would weigh approximately 1 billion tons. Not 1 billion tons distributed across a mountain range or an ocean basin or a continent. 1 billion tons contained in the volume of a kitchen utensil. A weight that, if somehow transported to Earth's surface, would sink through the crust, through the mantle, through the outer core, and come to rest at the center of the planet, pulling everything around it with gravitational consequences, we would notice immediately and not survive for long. That number is not an approximation rounded up for effect. It is a consequence of physics, of what happens when gravity compresses matter past every threshold that ordinary matter knows how to resist, past the strength of chemical bonds, past the resistance of electron clouds, past the pressure that holds atomic structure intact, all the way down to a state where the very identity of particles is renegotiated under conditions that exist nowhere else in the observable universe, except in these small, dense, spinning ancient objects drifting through the galaxy in aftermath of stellar catastrophe. A neutron star. To understand how something this extreme comes to exist, we need to begin at the end of a life. A massive star, perhaps 8 to 20 times the mass of our Sun, has spent millions of years burning through its nuclear fuel in the ordered sequence we described earlier. Hydrogen to helium, helium to carbon, carbon to neon oxygen silicon. Each stage shorter than the last, each requiring higher temperatures, each producing less energy per reaction, each bringing the star closer to the moment when the engine fails and gravity, patient and absolute, finally collects what it is owed. When the iron core collapses, as we described in the context of temperature, it does so in less than a second. The outer layers fall inward at a significant fraction of the speed of light, and then they hit something. The collapsing core in those first fractions of a second reaches nuclear density, the density of atomic nuclei themselves. At that point, the strong nuclear force, the force that holds protons and neutrons together inside nuclei, asserts itself against further compression. The core stiffens. It becomes, in effect, a single giant atomic nucleus, roughly 30 kilometers across, containing more mass than the Sun held up, not by fusion, not by thermal pressure, but by the quantum mechanical resistance of neutrons to being compressed into the same space. This resistance is called neutron degeneracy pressure. It is not a force in the conventional sense. It is a consequence of the Pauli exclusion principle, one of the fundamental rules of quantum mechanics, which states that no two identical fermions, particles like neutrons with half-integer spin, can occupy the same quantum state simultaneously. As neutrons are compressed closer and closer together, they run out of available quantum states. The pressure required to compress them further increases without limit. The core stiffens, and the infalling outer layers of the star rebound off that stiffened core in the shock wave that becomes the supernova explosion. What remains after the outer layers are blasted into space is the neutron star, a sphere of approximately 20 kilometers in diameter, containing between roughly 1.2 and 2.5 times the mass of the Sun, rotating rapidly, blazing with residual heat, threaded with magnetic fields of extraordinary strength, and governed by physics that has no analog in any environment accessible to ordinary human experience. 20 kilometers across, more massive than the Sun. To put that in perspective, the Sun is approximately 1.4 million kilometers in diameter. A neutron star with the same mass would be roughly 7,000,000 times smaller in diameter. If you could somehow replace the Sun with a neutron star of equal mass, Earth's orbit would be essentially unchanged. The gravitational pull at our distance would be the same, but the object at the center of our solar system would be smaller than many cities on Earth. It would be invisible to the naked eye at our current distance, a point of darkness where the Sun had been surrounded by the same planets on the same orbits as if nothing had happened except that the light had gone out. Gravity does not care about size, it cares about mass, and mass in a neutron star has been concentrated into a volume so small that the density at its surface defies ordinary intuition, and the density at its center may defy our current theories entirely. Let us talk about what the interior of a neutron star actually looks like, because the answer is both fascinating and genuinely uncertain in ways that reveal the current limits of physics. The outer layers of a neutron star, the crust, are composed of atomic nuclei arranged in a crystalline lattice, the densest solid known, surrounded by a sea of free electrons. This crust is extraordinarily strong. Estimates suggest it is roughly 10 billion times stronger than steel. It is the material that under certain conditions can crack and produce what astronomers call a starquake, a sudden readjustment of the crust that releases enormous energy in a burst of X-rays and gamma rays. We will return to starquakes shortly. Below the crust, the density increases and the neutrons dominate. Free neutrons no longer confined within atomic nuclei packed so closely together that their quantum wave functions begin to overlap. At these densities, theoretical models suggest the neutrons may enter a superfluid state, a quantum mechanical condition in which they flow without friction, carrying angular momentum with perfect efficiency. A neutron superfluid inside a spinning star. The implications of this for how neutron stars spin and slow down over time are still being worked out in research papers being written right now by physicists who spend their careers thinking about things that have no analog in any laboratory on Earth. Deeper still, the density climbs toward and beyond nuclear density, the density at the center of ordinary atomic nuclei. Here the models diverge. Some suggest that neutrons begin to dissolve at their boundaries, forming exotic structures called nuclear pasta, arrangements of nuclear matter, into sheets, tubes, and spheres with names like lasagna, spaghetti, and gnocchi. Physicists naming phases of ultra-dense nuclear matter after Italian food is either evidence of humor surviving at the frontier of knowledge or evidence that theoretical physicists are frequently hungry, possibly both. At the very center of a neutron star, if the mass is high enough, the density may exceed nuclear density significantly, and here, genuinely our theories run out of certainty. Some models suggest that quarks, the fundamental constituents of neutrons and protons, may become deconfined at these densities, forming a quark-gluon plasma, not unlike the state that filled the early universe in its first microseconds, but cold quark matter, a state of matter that, if it exists inside neutron stars, would make those objects among the strangest in the universe, hot on the outside, radiating X-rays, spinning rapidly, but harboring at their cores a form of matter last seen in the universe, a microsecond after the Big Bang. We do not know for certain whether this is true. The interiors of neutron stars are not directly accessible to any instrument we currently possess. We infer their properties from the outside, from how they spin, how they slow, how they emit, how they respond to perturbations, how they behave in the moments before merging with another neutron star. Each observation constrains the models a little further. Each constraint tells us a little more about what matter does at densities no laboratory can reproduce. This is one of the things that makes neutron stars so valuable scientifically. They are natural laboratories for physics that cannot be done any other way. The universe, in its indifference to our research agenda, has created conditions we cannot replicate and then left the evidence visible to our telescopes. Now let us add one more quality to the neutron star and watch what happens. Spin it faster. Many neutron stars rotate rapidly, some many times per second, as a consequence of angular momentum conservation during collapse. When a large, slowly rotating star collapses into a small, dense remnant, the way a spinning figure skater pulls in their arms to rotate faster, the rotation rate increases dramatically. Some neutron stars rotate hundreds of times per second. These are called millisecond pulsars, and they are among the most precisely regular objects in the universe. Their rotation rates are so stable that they rival atomic clocks in their consistency. Astronomers use them as tools to detect gravitational waves and test general relativity, because anything that disturbs the fabric of spacetime will leave a measurable imprint on the precise arrival times of the pulses they emit. A dead star, rotating 700 times per second, its surface moving at a significant fraction of the speed of light, serving as a natural clock precise enough to detect ripples in the geometry of reality. The universe recycles material with impressive functionality. But now let us add something else. Let us take a neutron star and give it a magnetic field, not merely strong, but incomprehensibly, extraordinarily violently strong. A magnetic field roughly 1,000 times stronger than an ordinary neutron star's, and 1,000,000,000,000 times stronger than Earth's. A magnetic field so intense that it stores more energy than most stars release over significant fractions of their lifetimes, coiled into the body of an object only 20 kilometers across. This is a magnetar, and magnetars are among objects that are not black holes, the most extreme things known to exist. We introduced magnetars briefly earlier in our journey through cosmic violence. Now let us stand closer and look more carefully, because in the context of density and extremity they deserve full attention. The magnetic field of a magnetar, ranging from roughly 10 to the 14 to 10 to the 15 Gauss, is so strong that it affects the physical vacuum itself. In ordinary empty space, electromagnetic fields have essentially no effect on the vacuum. But in fields of magnetar strength, a phenomenon called vacuum birefringence occurs. Empty space becomes optically anisotropic, meaning it bends light differently depending on the light's polarization. The vacuum, which we normally think of as the absence of anything, becomes a medium with measurable optical properties when subjected to these fields. This was predicted by quantum electrodynamics, the theory of how light and matter interact at the quantum level, decades before it was confirmed observationally. In 2016 observations of the neutron star RxJ 1856, 5 to 3754, using the European Southern Observatory's Very Large Telescope, detected a degree of polarization in the star's light consistent with vacuum birefringence, an observation of empty space behaving differently because of a magnetic field. Quantum electrodynamics, confirmed by staring at a dead star. The magnetic field of a magnetar also affects the atoms on its surface in the thin atmospheric layer if one exists above the crust. In a field of 10 to the 12 Gauss, comparable to ordinary neutron stars, hydrogen atoms are distorted into elongated shapes aligned with the field, their electron clouds stretched along field lines like a drop of water elongated by surface tension. In a magnetar field 10 to 1,000 times stronger, atoms as we normally understand them may cease to exist in any recognizable form. The electrons are so tightly confined to motion along field lines that the chemistry of a magnetar surface, if chemistry is even the right word, bears no resemblance to the chemistry of any environment accessible to ordinary experience. You could not place any familiar substance on the surface of a magnetar and expect it to behave in any familiar way. Not because it would melt or vaporize, though it would instantly catastrophically, but because the fundamental interactions between atoms that we call chemistry would be operating under rules so altered by the magnetic field that the results would be unrecognizable. Matter near a magnetar is not matter as we know it. Now let us talk about starquakes, because they are among the most direct evidence we have for the extraordinary mechanical properties of neutron star crusts. As a neutron star ages, it spins down. The magnetic field acts as a brake, radiating away rotational energy. As the star slows, it becomes slightly less oblate, slightly more spherical, because the centrifugal force pushing the equator outward is reducing. The crust, that extraordinarily strong crystalline lattice, 10 billion times stronger than steel, must adjust to the changing shape. It builds stress. It accumulates strain over centuries or millennia. And then occasionally, suddenly, it cracks. The energy released in a magnetar starquake can be enormous. The giant flare observed on the 27th of December 2004 from the magnetar SGR 1806-20 released more energy in approximately 0.2 seconds than our sun emits in approximately 2500000 years. That number has been written in this script, and it will be read aloud, and it will be heard, and the appropriate response is to simply let it sit for a moment before continuing. More energy than the sun produces in 2500000 years, in 0.2 seconds. From an object 20 kilometers across, the flare was so intense that despite originating approximately 500,000 light-years away on the far side of the Milky Way, it measurably ionized Earth's upper atmosphere. Satellites detected the surge. Radio communication was briefly disrupted on the side of Earth facing the magnetar at the time. An object smaller than a city halfway across the galaxy left a detectable mark on our planet's atmosphere. What would it have been like closer? The answer is not difficult to calculate, and the answer is not survivable. Within a few light years, the radiation environment would be fatal to any unshielded biological material. Within a light year, catastrophic. At the distance of the nearest star system, approximately 4 light-years from Earth, the flare would have delivered a radiation dose capable of causing significant atmospheric damage to a planet like ours. Fortunately, no known magnetar is positioned that close. The universe, as we have noted before, tends to arrange its most dangerous objects at considerate distances. This is not courtesy, it is probability and geometry. Space is vast, magnetars are rare, and the nearest known ones are hundreds to thousands of light years away. We observe them safely. We measure their flares with instruments. We build models of their interiors. We test quantum electrodynamics against their polarized light. We use them, in other words, as data. As natural experiments in physics, we cannot perform any other way. That is the appropriate relationship with a magnetar. Now, let us pull back from the magnetar and consider density one final time before we move forward, because there is a boundary beyond the neutron star that represents the ultimate destination of compressed matter, a place where density does not merely reach extreme values, but becomes, in a sense, undefined. A place where our measure of density mass divided by volume breaks down because volume itself becomes a troubled concept. A black hole. We have discussed black holes at length in the context of violence and feeding and merging. But in the context of density, they deserve a specific moment because the singularity at the heart of a black hole, if our current theories are taken, literally represents infinite density. All the mass of the collapsed object concentrated into a point of zero volume. Physicists are generally suspicious of infinities when they appear in physical theories. Infinities usually signal not a real physical condition, but a breakdown in the theory being applied. A place where the framework stops working and a better framework is needed. The singularity of a black hole is widely believed to be exactly this kind of signal. It tells us that general relativity, the theory that predicts it, is incomplete. That at the densities and curvatures found at the center of a black hole, a theory of quantum gravity is needed that we do not yet possess. So in some sense, the densest place in the universe is also the place where our description of density itself fails, where matter has gone somewhere our mathematics cannot clearly follow, where the frontier of physics is not merely distant, but actively present, hidden behind an event horizon unreachable by any instrument, protected from our curiosity by the fundamental geometry of curved spacetime. We know it is there. We cannot see it. We cannot describe it fully. We can only stand outside the horizon measuring what the region around it does, inferring the presence of the thing we cannot reach. There is something almost meditative about that. The densest place in existence, the ultimate compression of matter hidden permanently from direct observation, knowable only through its effects on everything around it, present but unreachable, real but indescribable. The universe keeps its deepest secrets well. Let us rest here for a moment and take stock of what the densest places in the universe have shown us. A neutron star contains more mass than our Sun in a sphere smaller than most cities. Its crust is 10 billion times stronger than steel. Its interior may harbor superfluid neutrons and exotic nuclear matter, and possibly at the very center, a form of matter last seen a microsecond after the Big Bang. Its magnetic field, in the extreme case of a magnetar, is strong enough to distort empty space and release more energy in fractions of a second than the Sun produces in hundreds of thousands of years. And beyond the neutron star, the black hole, where density loses its meaning, where spacetime curves so severely that the usual rules of geometry no longer apply, where our best theory of gravity reaches its limit and admits honestly that it does not know what comes next. These places exist. They are not theoretical constructs. They are measured. They are catalogued. There are dozens of known magnetars in the Milky Way. There are stellar mass black holes throughout the galaxy. There is a supermassive black hole at the galactic center, 26000 light-years away, containing 4 million solar masses in a region smaller than our solar system currently. Quiet, currently patient, currently doing what gravity does when there is nothing nearby to consume. Waiting. And all of this, the cold clouds, the hot stellar cores, the supernova temperatures, the quasar accretion disks, the neutron star densities, the magnetar flares, all of it is in some sense preparation. Preparation for the places where all of these extremes converge simultaneously, where temperature and density and violence and speed all reach their maximum values in the same place at the same moment. We are heading toward the most violent intersections in the observable universe. The places where neutron stars meet, where matter is destroyed and created in the same instant, where the heaviest elements are forged in conditions that exist for fractions of a second, and then are gone, where gravitational waves roll outward through space-time, carrying the news of what happened to any instrument sensitive enough to hear. We are heading toward collision. And what happens there is worth every cold cloud, and every hot core, and every dense remnant we have passed through to reach it. There is a binary star system in the constellation Aquila, approximately 210,000 light-years from Earth, called PSRJ 1915 plus 1606. It was discovered in 1974 by Russell Hulse and Joseph Taylor at the Arecibo Observatory in Puerto Rico, using a radio telescope with a dish 305 meters across, built into a natural depression in the landscape of a Caribbean island, pointed at the sky with the patience that radio astronomy requires. What Hulse and Taylor found was a pulsar, a rapidly rotating neutron star emitting precise radio pulses, orbiting another neutron star in a tight binary system. The orbital period at the time of discovery was approximately 7 hours and 45 minutes. The two neutron stars were circling each other at a distance smaller than the diameter of our Sun. This was already extraordinary. But what made it historic was what happened over the following years as Hulse and Taylor continued to monitor the system with extraordinary precision. The orbital period was shrinking. The two neutron stars were spiraling inward, and the rate at which they were spiraling inward matched with remarkable precision the prediction made by general relativity for a system losing energy through the emission of gravitational waves. This was the first indirect evidence that gravitational waves were real. That Einstein's prediction made in 1916 that accelerating masses disturb the fabric of spacetime and send ripples outward at the speed of light was not merely a mathematical consequence of the equations, but a physical reality playing out in the universe. Hulse and Taylor received the Nobel Prize in Physics in 1993. The system they discovered continued to spiral inward, the two neutron stars drawing closer orbit by orbit, year by year, decade by decade. By now, tens of millions of years from the moment of discovery, PSRJ 1915 plus 1606 will have completed its inspiral. The two neutron stars will have met. They will have merged in a fraction of a second, releasing energies that dwarf anything we have described so far in our journey through extremes. And no one will be there to watch. But we have watched others. On the 17th of August, 2017 at 124104 UTC, the LIGO gravitational wave detectors in Hanford, Washington and Livingston, Louisiana registered a signal, not the brief chirp of two black holes merging which lasts a fraction of a second and then is gone, something longer, something that swept upward in frequency over approximately 100 seconds. A gravitational wave signal climbing through the LIGO band as two objects spiraled together in their final moments. The signal was consistent with two neutron stars. Objects, each roughly 1.1 to 1.6 times the mass of the Sun, compact enough to have been spiraling together for millions of years now, in their last 100 seconds of independent existence, racing around each other dozens times per second, the gravitational waves growing stronger and higher in frequency as the orbital period shrank, as the distance between them collapsed from hundreds of kilometers to tens of kilometers to single digits to zero. Approximately 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of sky. A burst of gamma radiation lasting approximately 2 seconds, arriving from a direction consistent with the gravitational wave source with a time delay of 1.7 seconds, consistent with the difference in travel time between gravitational waves and light, or with a brief delay between merger and jet formation. Within hours, optical telescopes around the world had found the source. A faint, rapidly brightening and then fading glow in the galaxy NGC 4993, approximately 130 million light-years away in the constellation Hydra. A kilonova. The visible light signature of the neutron star merger's aftermath, powered by the radioactive decay of freshly synthesized heavy elements scattered into space by the collision. The event was catalogued as GW170817. It was the first time in human history that a single astrophysical event had been observed simultaneously through gravitational waves and electromagnetic radiation, through the rippling of spacetime itself and through light. Through two entirely different senses that humanity had only recently developed the instruments to use. For the first time, we did not merely see a cosmic event, we felt its geometry. Now let us stand inside those final 100 seconds and try to understand what was actually happening. The two neutron stars in GW170817 had been orbiting each other for an estimated billion years before their final merger. A billion years of slow in spiral, a billion years of gravitational waves carrying away orbital energy in quantities too small to measure directly at the distances involved, but cumulative, patient, inevitable. Over that billion years, the two objects had drawn close enough that their final in-spiral would take only 100 seconds from the moment the gravitational waves entered the LIGO band to the moment of merger. In those final 100 seconds, the orbital velocity of the neutron stars was climbing toward a significant fraction of the speed of light. The gravitational waves they emitted were carrying away energy at an increasing rate. The tidal forces each star exerted on the other were beginning to distort their shapes, stretching them slightly toward each other. The dense nuclear matter of each object beginning to feel the gravitational gradient imposed by its companion. In the final seconds, the stars were orbiting each other hundreds of times per second. The space between them was measured in kilometers. The tidal distortion was significant. Material may have been streaming between them. The magnetic fields of two neutron stars, already extraordinarily strong, were interacting, twisting, amplifying, and then, in a fraction of a second, they merged. The combined mass of the two stars, now occupying a single region of space, underwent a catastrophic reconfiguration. If the total mass was below the maximum that neutron degeneracy pressure can support, the result may have been a hypermassive neutron star, a rapidly rotating object temporarily supported against further collapse by centrifugal force, nuclear pressure blazing with energy, living perhaps milliseconds or seconds before its rotation slowed enough for gravity to win and a black hole formed. If the mass was above that threshold from the beginning, the collapse to a black hole may have been essentially immediate. Either way, the environment around the merger was extraordinary. Temperatures in the merged object and its surrounding debris reached hundreds of billions of Kelvin. Densities exceeded nuclear density. Neutrinos flooded outward from the hot, dense core in numbers that briefly rivaled the energy output in any other form. Magnetic fields in the debris disk surrounding the remnant were amplified to magnetar-like strengths. And in the polar regions, if the geometry and conditions were right, a jet formed. A narrow beam of plasma and radiation, accelerated to within a fraction of a percent of the speed of light, punched outward through the surrounding debris and into open space. That jet, arriving at Earth 130 million years later, was the short gamma-ray burst detected by Fermi, the brief violent announcement of a merger that had occurred when the most complex life on Earth was single-celled organisms in ancient oceans. Now, let us talk about what the merger made, because in addition to gravitational waves and gamma rays and a jet, the neutron star collision in GW170817 made something else. Something that in the context of human history carries a weight that is almost uncomfortable to consider. In the hot, neutron-rich debris disk surrounding the merger remnant, a process occurred that had been theorized for decades, but never directly confirmed until that night. Atomic nuclei in the disk were flooded with free neutrons. Moving rapidly through this neutron-rich environment, nuclei captured neutrons faster than they could decay. Within fractions of a second to seconds, nuclei built up through rapid successive neutron captures, climbing the table of elements past iron, past the limits of ordinary stellar nucleosynthesis, into the regime of heavy elements: gold, platinum, silver, lead, uranium, osmium, iridium, strontium. In the hours and days following the merger, the kilonova glow was analyzed by spectrographs attached to telescopes around the world. The spectra showed signatures of strontium, confirmed directly, and evidence consistent with a range of other heavy R-process elements. The observations matched theoretical predictions for kilonova emission powered by the radioactive decay of freshly synthesized heavy elements with extraordinary precision. The merger of two neutron stars had been observed to produce gold. The amount of gold synthesized in GW 170817 alone has been estimated at anywhere from a few to perhaps 10 times the mass of Earth. 10 Earth masses of gold created in fractions of a second in the debris of two colliding dead stars, 130 million light-years away. Now consider what that means for the gold that exists in our solar system. The gold in Earth's crust. The gold in the rings people exchange at weddings. The gold in the circuits of the devices through which this script might eventually be heard. That gold did not form in the sun. It did not form in any ordinary stellar process. It formed billions of years before the solar system existed in events like GW 170817. In neutron star mergers that scattered their heavy element debris into the interstellar medium, where it mixed with gas and dust over billions of years until gravity gathered it into a new solar nebula and the planets formed from that enriched material. Every gram of gold on Earth is the remnant of a cosmic catastrophe. Every ring, every coin, every circuit, every gilded surface, every treasure hoarded and every treasure lost, all of it traces back to the final second of two neutron stars ending their billion-year dance in temperatures of hundreds of billions of Kelvin and densities, exceeding nuclear matter, and a flash of gamma radiation that crossed 130 million light-years to be recorded by a telescope, named Fermi, floating in Earth orbit on an August morning in 2017. That is not mythology, that is astrophysics. But neutron star mergers, as extraordinary as GW 170817 was, are not the only violent intersections the universe arranges. There are other places where extremes converge. Other moments when the ordinary separation between hot and dense, and fast and energetic collapses, and all of those qualities arrive at the same address simultaneously. One of the most dramatic of these is the tidal disruption event, a moment when a star wandering too close to a supermassive black hole is torn apart by tidal forces and consumed. We mentioned tidal disruption events briefly before. Now, let us stand closer. A star approaches a supermassive black hole. Perhaps it has been nudged onto a new orbit by a gravitational interaction with another star in the dense stellar environment near the galactic center. Perhaps it has simply been drifting on an elliptical path for millions of years, and this is the passage that brings it inside the tidal disruption radius. Whatever the cause, at some point the star crosses a threshold. The tidal force exerted by the black hole across the diameter of the star, the difference in gravitational pull between the near side and the far side, exceeds the self-gravity of the star that holds it together. The star is unbound. It does not fall straight in. The material has angular momentum. It stretches into a long stream wrapping around the black hole, with roughly half the stellar material falling inward and half being ejected outward. The infalling material forms an accretion disk that heats rapidly to extreme temperatures, pouring out radiation across the electromagnetic spectrum. For weeks to months, the flare can outshine the host galaxy, a single star's death, briefly rivaling the combined light of hundreds of billions of others. The temperatures in the inner accretion disk of a tidal disruption event can reach millions to tens of millions of Kelvin. The luminosity can approach or exceed the Eddington limit, the theoretical maximum luminosity for a given mass, above which radiation pressure would blow away the infalling material. At the Eddington limit, the outward pressure of radiation exactly balances the inward pull of gravity. Some tidal disruption events appear to exceed this limit briefly, in ways that are still being studied and debated. And in some tidal disruption events, jets form, narrow relativistic beams launching outward from the poles of the system, detectable across enormous distances. In 2011, a tidal disruption event called SWIFT-J 1644+57 was observed, producing a jet pointed almost directly toward Earth, allowing astronomers to study the launching and evolution of a relativistic jet in real time, in a way that had not been possible before. a star likely similar in mass to our Sun, torn apart by a supermassive black hole producing a jet aimed at Earth. Observed live, studied, measured, added to the catalogue of things the universe does when matter approaches the wrong object at the wrong distance. Now, let us return to gamma-ray bursts one final time, because in the context of violent intersections, they represent the convergence of the most extremes in the smallest time. A long gamma-ray burst associated with the collapse of a massive, rapidly rotating star into a black hole can release more energy in its prompt emission phase, typically lasting seconds to minutes, than our Sun will emit over its entire 10 billion-year lifetime. That energy is concentrated into a jet only a few degrees wide. If you are not in the path of that jet, you may detect little. If you are looking at one of the most energetic events in the observable universe. The mechanism requires a remarkable alignment of conditions. The star must be massive enough to form a black hole rather than a neutron star. It must be rotating rapidly enough that the collapsing core forms an accretion disk rather than falling directly into the black hole. The magnetic field must be oriented correctly to launch a jet. The jet must be powerful enough to punch through the outer layers of the dying star rather than being choked by them. And it must be aimed in the right direction to be detected at astronomical distances. When all of these conditions align, the result is something that briefly burns brighter than a galaxy of 100 billion stars. A single dying star in its final seconds, outshining the combined light of everything else in its cosmic neighborhood. GRB 080319b, a gamma-ray burst detected on the 19th of March, 2008, originating approximately 7.5 billion light-years away, was briefly visible to the naked eye from Earth. In the middle of the day, if you had known where to look, you could have seen with your unaided eyes a star dying 7.5 billion light-years away. The light from that event left its source before the Earth existed. It crossed more than half the observable universe. And then it arrived here, bright enough to see with the eyes evolution gave you for navigating a savanna. The universe occasionally arranges things that should not be possible by any intuitive measure, and then it simply does them. Now let us stand back from all of these violent intersections and notice something they share. Every one of them involves a threshold crossing, a moment when balance fails and a new state emerges. The neutron-star merge are two objects orbiting each other for 1 billion years, then crossing the threshold of contact in a fraction of a second. The tidal disruption event, a star drifting through space for millions of years, then crossing the tidal disruption radius and being unmade in weeks. The gamma-ray burst, a star burning steadily for millions of years, then crossing the threshold of core collapse in less than a second. Long preparation, sudden crossing, irreversible transformation. This pattern is not unique to astrophysics. It appears in phase transitions where water cools steadily until it crosses 0 degrees and becomes ice in a sudden reorganization of molecular structure. It appears in geology, where tectonic stress accumulates over centuries before releasing in seconds of earthquake. It appears in biology, where gradual environmental pressure accumulates until a species population collapses or adapts in ways that seem sudden from any individual's perspective. The universe has a preference for this pattern: slow accumulation, threshold, rapid transformation, and often in that transformation, the creation of something that could not have existed in the previous state: gold from neutron star merger debris, new stars from supernova shockwaves, gravitational wave astronomy from the merger that provided its most dramatic early confirmation. The most violent moments are often the most generative ones. Now, there is something else worth noting about these intersections. They are rare. Not every star becomes a gamma-ray burst. Not every neutron star binary merges on a timescale we can observe. Not every star wandering near a galactic center crosses the tidal disruption radius. The universe is large and old and produces these events at rates that make them extraordinary rather than routine. In the observable universe, perhaps one gamma-ray burst occurs per galaxy per million years. Neutron star mergers are similarly rare on human timescales, though abundant in cosmic ones. Rarity matters. Not every system reaches the conditions for extreme intersection. Most stars live and die in relative quiet. Most neutron stars spin down slowly without ever finding a partner. Most galactic centers sit without a wandering star to disrupt. The violent intersections are outliers, the far tail of the distribution, the places where multiple conditions align simultaneously in the way that is required for something extraordinary to happen. But the universe is large enough and old enough that even rare events are common in absolute terms. Somewhere in the observable universe right now, a short gamma-ray burst may be occurring. Somewhere a tidal disruption event is brightening. Somewhere, two neutron stars are in their final seconds of inspiral approaching the moment when two dense remnants of dead stars will merge and in their collision forge the heavy elements that may one day become part of a planet. None of it is aimed at us. None of it requires our attention. None of it is happening on a timescale that places any demand on your evening. These events are simply occurring as they have been occurring throughout the history of the universe, as they will continue to occur long after every star that burns today has exhausted its fuel and gone dark. And they are happening in silence. No sound crosses the vacuum. No thunder rolls between galaxies. The merger of two neutron stars releasing more energy in a fraction of a second than the Sun will produce in its lifetime arrives at Earth as a tiny perturbation in the length of laser beams in a detector in Louisiana, as a spike on a graph, as a signal that required decades of instrument development and thousands of scientists to build the sensitivity to detect. The loudest things in the universe whisper when they reach us. There is a comfort in that. Not because violence is comfortable, but because distance transforms it. Because the universe is large enough that its most extreme events can happen constantly everywhere and arrive here as nothing more than data, as information, as the raw material of understanding rather than the raw material of harm. We are far enough away from the violence to appreciate it. That distance is a gift we did not earn and should not take for granted. Pull back from the neutron-star merger. Pull back from the gamma-ray burst and the tidal disruption event and the accretion disk blazing at millions of Kelvin. Pull back past the galaxy that hosted GW170817 past NGC 4,993 inches Hydra, past the local group of galaxies, of which the Milky Way is a member, past the nearest galaxy clusters, past the large-scale structures we can resolve into individual components. Keep pulling back. At some point, something changes. The galaxies, which had been distributed in threads and sheets and clusters, the vast cosmic web of filaments we described earlier, begin to thin. The threads become sparse. The clusters recede into the distance. And between them, growing larger and more dominant as the scale increases, appear the voids, the enormous dark, nearly empty regions that occupy the majority of the universe's volume. Space is so large and so empty that the word empty, by the time you have applied it to them honestly, has been stretched almost beyond its ordinary meaning. We have spent most of our journey tonight in the presence of extremity, extreme cold, extreme heat, extreme density, extreme violence. The universe at its most concentrated, most energetic, most catastrophically active. Now we are going to visit the universe at its most absent. And the emptiest places in existence are in their own way as extreme as anything we have encountered. Not because of what they contain, but because of what they do not. Not because of what happens there, but because of how completely, how profoundly, how permanently nothing happens there. The voids are a different kind of limit. Not the lower limit of temperature, not the upper limit of density, but the lower limit of presence itself. The places where the universe has spread itself so thin that the concept of a cosmic neighborhood becomes inapplicable, where a galaxy, if one existed there, would look out in every direction and find nothing, not the friendly nothing of a clear night sky, where stars are merely distant, but a nothing measured in hundreds of millions of light years, a nothing that has persisted for billions of years and will persist for billions more, a nothing so complete that it constitutes in its own right one of the most extreme environments the universe contains. The large-scale structure of the universe is one of the most beautiful and disorienting things cosmology has revealed. On scales of tens of millions of light years and above, the distribution of matter is not uniform. It is not random. It is structured in a way that resembles with uncanny accuracy a three-dimensional foam or sponge, or the delicate tracery of a spider's web stretched across distances that humiliate the imagination. Matter is concentrated into filaments long threads of galaxies and galaxy clusters connected end-to-end across hundreds of millions of light-years. Where filaments intersect superclusters form the densest nodes in the cosmic web, containing thousands of galaxies bound together in the largest gravitationally bound structures in existence. The filaments and nodes form the walls and edges of enormous polyhedral cells, and the interiors of those cells are the voids. The voids are not perfectly empty. They contain some galaxies, typically fewer, smaller, and less clustered than galaxies in filaments. They contain diffuse gas. They contain dark matter, though, at densities far below the cosmic average. They are underdense rather than truly empty in the strict sense, but underdense on a scale that strains the prefix. The average density inside a large cosmic void may be 10 to 20% of the cosmic mean density or lower. In the largest voids, it may be even less. Regions where the universe has, through the action of gravity, pulling matter outward toward the denser filaments, over billions of years been evacuated of most of its contents, and they are large. The typical cosmic void has a diameter of tens to hundreds of millions of light-years. The largest known voids approach and, in some cases, exceed 1 billion light-years across. 1 billion light-years. A sphere of space, 1 billion light-years in diameter, containing almost nothing. For context, the entire observable universe is approximately 93 billion light-years in diameter. A single void can occupy a significant fraction of that volume and contain in its interior almost no galaxies, almost no stars, almost no chemistry, almost no possibility of the kind of organized complexity that eventually produces things like awareness and curiosity and the impulse to ask what is out there. The most famous individual void has a name, the Boötes void. It lies in the direction of the constellation Boötes, approximately 700 million light-years from Earth, and it is approximately 330 million light-years across. It was discovered in 1981 by Robert Kirshner and colleagues during a survey of galaxy redshifts when they found an enormous region of sky containing far fewer galaxies than expected, a hole in the distribution of matter where the survey found in a region they expected to be populated almost nothing, 330 million light-years across. If the Milky Way were located at the center of the Boötes void, the nearest neighboring galaxy outside the void would be approximately 165 million light-years away. Our nearest large galactic neighbor, the Andromeda Galaxy, is approximately 2.5 million light-years from Earth. If we were in the Boötes void, the nearest equivalent would be 66 times farther. The night sky from a planet inside the Boötes void would contain far fewer galaxies visible to any telescope. The cosmic web, that structure of filaments and clusters that defines the large-scale architecture of the universe, would be visible only at the void's distant edges. A faint suggestion of something denser, something more connected somewhere far away in every direction. The isolation would not be absolute. Some galaxies exist even in large voids, but it would be profound. A civilization arising inside a cosmic void would have a very different cosmological perspective than we do. They might look outward with their most powerful telescopes and see the edges of their void as the boundary of the known universe, before eventually realizing that beyond that boundary lay the full cosmic web, the filaments and clusters and superclusters. The majority of the universe's matter, concentrated in a shell around their extraordinary emptiness. They might for a long time believe they lived in an unusually sparse universe. They might not immediately realize that their location was the exception rather than the rule. We are fortunate to live in a relatively normal location, a galaxy embedded in the outskirts of a supercluster surrounded by a cosmic neighborhood dense enough to be interesting. We can look out and see the structure. We can map the voids and the filaments. We can understand our place in the web because we are not so deep inside a void that the web is invisible. That perspective is not something we earned. It is simply where the solar system happened to form. Now let us think about what the voids mean physically, because they are not merely absences. They are active environments in the sense that their emptiness is a consequence of ongoing physical processes and will continue to evolve over cosmic time. The voids are empty because gravity is efficient. In the early universe, matter was distributed nearly uniformly with tiny fluctuations, the quantum variations amplified by inflation that we discussed earlier. Regions slightly denser than average attracted more matter over time. Regions slightly less dense than average lost matter to their denser neighbors. Gravity amplified the initial fluctuations, turning small differences into large ones, turning slight overdensities into filaments, and clusters turning slight underdensities into voids. This process, called gravitational collapse on large scales, is still ongoing. The voids are still growing. Galaxies at the edges of voids are still being pulled outward toward the surrounding filaments by the gravitational attraction of the denser material there. The voids are expanding into themselves, not because space inside them is expanding faster, but because the matter that once populated their interiors has been drawn away. The emptiness is deepening, slowly, imperceptibly on human timescales, but measurably on cosmological ones. And dark energy is helping. The accelerating expansion of the universe, driven by whatever dark energy actually is, stretches space uniformly. In the densest regions, gravity is strong enough to hold structures together against this expansion. Galaxy clusters remain bound, filaments remain coherent. But in the voids where gravity is weak and matter is sparse, the expansion is less resisted. The voids expand more freely. They grow. The matter at their edges is drawn not only toward neighboring filaments, but also stretched away from void centers by the expansion itself. Over the long future of the universe, the voids will become increasingly dominant. As the expansion accelerates, the filaments and clusters will remain as islands of matter, but the spaces between them will grow. The universe will become on average emptier. The cosmic web will remain, but its nodes will be farther apart, the distances between them stretching beyond the reach of any signal, any traveler, any possibility of connection. The universe is in the process of isolating itself. Slowly, over billions of years, the expansion is drawing regions of space apart faster than light can cross the growing distance. Galaxies beyond a certain radius from us, called the cosmic event horizon, are already receding faster than light, and are therefore permanently beyond our reach. That horizon is not fixed, it is moving. More and more of the universe is crossing beyond it as the expansion continues. In the far future, the observable universe will shrink, not because matter is disappearing, but because the expansion is carrying it beyond the limit of causal contact. The loneliness of the cosmic voids is a preview of the universe's ultimate fate. Now let us go inside a void and simply be there for a moment. Not inside the Boötes void, which at 330 million light-years across is too large for any analogy to contain comfortably. Let us imagine a smaller void, one of the many voids of tens of millions of light-years that populate the cosmic web like bubbles in foam. Let us imagine a galaxy near its center, a galaxy perhaps not unlike the Milky Way in structure, and content orbiting a star, not unlike our sun on a planet with an atmosphere and an ocean, and something looking at the sky. That sky would be dark. Not the dark of a clear night away from city lights with its thousands of visible stars and the faint band of the Milky Way arching overhead. The stars of its own galaxy would be there. The structure of the galaxy itself would be visible just as it is from Earth. But the extragalactic sky, the sky beyond the Milky Way equivalent, would be notably emptier than ours. No Andromeda galaxy approaching in a great smear of light. No Magellanic clouds hanging in the southern sky. The nearest large galaxies would be far away at the void's edge, visible only as faint smudges in long exposure images. The deep sky surveys from that world would show a different picture than ours. The cosmic web would be evident, but distant. The filaments and clusters would appear as a kind of shell at the edges of the survey, a concentration of structure at the boundaries of the void, and then a long emptiness between that shell and the home galaxy at the center. It would be beautiful in the way that vast empty spaces can be beautiful, the way the open ocean is beautiful from a small boat, the way a desert at night is beautiful with the stars overhead and nothing in any direction for as far as movement could take you. Beautiful and spacious and extraordinarily quiet. But it would also be in a subtle and specific way lonely, not emotionally lonely, assuming the beings doing the looking were capable of emotional loneliness, though that is an interesting assumption. Cosmologically lonely, physically isolated, Located in a region of the universe where the density of matter is far below average, where the nearest large structures are far away, where the cosmic web announces itself only at the periphery of observation. We do not live in such a place. We live in the outskirts of the Virgo supercluster, part of the larger Laniakea supercluster, embedded in the cosmic web with neighbors in multiple directions. Our deep sky surveys show filaments and clusters and voids in a rich three-dimensional structure. We can see both kinds of large-scale environment from where we are. We can map the dense and the empty and understand our position between them. That vantage point is not guaranteed. It is not universal. It is local, and it is in its own quiet way fortunate. There is one more aspect of the voids that deserves attention before we begin our final descent back toward the human scale, and it concerns what the voids might contain that we cannot see. Dark matter, as we discussed earlier, is inferred from gravitational effects rather than observed directly. In the filaments and clusters, dark matter halos surround and permeate the visible structures, providing the gravitational scaffolding on which galaxies are built. In the voids, dark matter is present too, though, at lower densities than in the filaments. But there is another invisible component even more poorly understood: dark energy. Whatever dark energy is, it appears to be a property of space itself, an energy density associated with the vacuum that causes the expansion of the universe to accelerate. It does not cluster like matter. It does not concentrate in filaments or avoid voids. It is present everywhere uniformly, as far as current observations can determine. In the densest galaxy clusters and in the emptiest voids alike, dark energy is present at the same density. This means that in the voids where matter density is low, dark energy is proportionally more dominant than anywhere else in the universe. The voids are not merely empty of matter. They are, in a sense, the places where dark energy is most purely expressed, where the vacuum itself, with its mysterious accelerating influence, operates with the least competition from ordinary and dark matter combined. We do not know what dark energy is. We do not know whether it is truly a constant property of the vacuum, as Einstein's cosmological constant suggests, or whether it varies over time and space in ways our current observations cannot yet detect. We do not know whether it will remain at its current strength, or whether it will grow, potentially driving an accelerating expansion so extreme that eventually even atomic nuclei are torn apart in an event theorists call the Big Rip. We do not know whether it reflects some fundamental property of quantum fields, or some modification of gravity, or something genuinely new. We only know that it is there, that it is causing the universe to expand faster and faster, and that its dominance is most pure in the emptiest places, in the voids. In the great dark spaces between the filaments, where almost nothing exists except space itself, expanding, carrying whatever small amount of matter remains within the void to ever greater distances from its neighbors, the emptiest places are full of the thing we understand least. That is perhaps the most honest summary of what the voids have to teach us. Not that emptiness is simple, not that absence is the same as understanding, but that even in the places where the universe seems most transparent, most reduced, most stripped of complexity, there are layers of ignorance waiting to be uncovered. The voids are not nothing. They are the universe's largest question marks. Now let us notice something about the journey we have taken tonight. We began in the cold, in the Boötes Nebula, at 1 Kelvin, barely above absolute zero, a dying star exhaling its last warmth into space. We climbed through molecular clouds where stars are born in the patient dark. We ascended through stellar temperatures from photosphere to core from thousands to millions of Kelvin, and then we kept climbing through supernova cores and quasar accretion disks and the early universe itself until we reached the edge what our physics can describe. We descended into density, into the neutron star interior, where nuclear matter gives way to exotic states, where the crust is 10 billion times stronger than steel, and a teaspoon of material weighs 1 billion tons. We stood beside magnetars whose fields distort the vacuum and whose starquakes release more energy in fractions of a second than the sun produces in hundreds of thousands of years. We witnessed the violent intersections, the neutron star merger that forged gold and announced itself in gravitational waves and gamma rays simultaneously. the star torn apart by a black hole, the dying massive star whose final second outshone a galaxy. And now we have arrived here in the voids, in the emptiest places, in the dark spaces between the filaments where the cosmic web grows thin and the universe expresses its most dominant component, dark energy, most purely. Where the isolation is measured not in light years, but in hundreds of millions of light years. Where the silence is not merely the silence of vacuum, but the silence of genuine absence. The full range of the universe, from the densest to the emptiest, from the hottest to the coldest, from the most violently active to the most profoundly still, has passed through our attention tonight like a long, dark, extraordinary river. And now there is one more thing we need to do. We need to come home, because the journey through these extremes was never really about the extremes themselves. It was about what they mean for the small, warm, temporary, extraordinarily improbable fact of your existence in the middle of all of it. It was about the chain of physical events running from the first fractions of a second of the universe's history through 14 billion years of stellar evolution and element synthesis and planetary formation and chemical complexity that connects the hottest places in the early universe to the quiet room where you are resting right now. That chain is real. It is physical. It is documented in the isotopic composition of your bones and the nuclear history of the iron in your blood and the quantum mechanical behavior of the carbon bonds that hold your cells together. You are not a spectator of the universe's extremes. You are their downstream consequence. And that is where we are going next. There is a question that has been waiting patiently at the edge of everything we have discussed tonight. Not a scientific question exactly, not the kind with a numerical answer or a reference to a specific observation or a citation from a published paper, but a question that the science keeps pointing toward the way shadows point toward light, the way rivers point toward the sea. A question that becomes unavoidable once you have stood beside the coldest place in the observable universe and the hottest and the densest and the most violent and the most empty, and looked at all of them honestly. The question is simple. How are you here? Not in the sense of which hospital and which year and which set of circumstances brought you into existence as a social and biographical fact. Those answers matter, and they belong to you, and they are not what we are asking. We are asking the deeper version, the physical version, the version that the universe itself seems to be quietly posing every time we trace the chain of events backward from a living, breathing, wandering creature to the conditions that made it possible. How in a universe that is mostly cold vacuum, that is mostly empty space between filaments of matter, that is mostly darkness and radiation, and extremes incompatible with any chemistry we would recognize as life-sustaining, how does something like you come to exist? The answer is long. It took 14 billion years to assemble, and tonight, without quite stating it directly, we have been walking through its chapters. It begins with the temperature. Not the temperature of today's universe, cool and structured and hospitable in certain narrow pockets, but the temperature of the universe at its beginning, the 100 billion Kelvin of the first second, the trillion Kelvin of the first microsecond, the unimaginable heat of the Planck epoch, where our theories reach their limit and admit they cannot see further. From that heat, as the universe expanded and cooled, the first particles condensed. Quarks bound into protons and neutrons combined into light nuclei, hydrogen and helium and traces of lithium forged in the first 3 minutes in the furnace of the entire young cosmos, poured into the expanding space as the raw material of everything that would follow. That primordial hydrogen is still here. It is in the water in your body. It is in the organic molecules of your cells. It is in the air you breathe. The hydrogen in you is 14 billion years old. It was synthesized when the universe was 3 minutes old. It has been part of countless other things in the intervening time, part of gas, clouds and stars and planetary oceans and other living creatures, and the interstellar medium, and perhaps other stars again, before ending up here, in this configuration in this moment. Your hydrogen is older than the Earth, older than the Sun, almost as old as time itself. Then the cold came, As the universe expanded and cooled over hundreds of millions of years, that primordial hydrogen gathered into the molecular clouds we visited at the beginning of our journey. Cold clouds at 10 to 30 Kelvin, barely above absolute zero, drifting in the dark between regions where the cosmic web was beginning to define itself. And in those cold clouds, gravity did its patient work. Overdensities collapsed, protostars formed. The first stars ignited. Those first stars, called population 3 stars, were different from the stars we know today. They formed from gas that contained almost no heavy elements, only hydrogen and helium and traces of lithium. Without the cooling effect of heavy elements like carbon and oxygen, the clouds that formed them could not fragment into small pieces easily. The first stars were likely massive, perhaps hundreds of times the mass of the Sun. They burned hot and fast and died young, in supernova explosions that scattered the first heavy elements into the surrounding universe. Carbon, oxygen, nitrogen, the elements of organic chemistry, the elements without which biology as we know it is not possible. They did not exist before those first stars. They were made in stellar cores and distributed by stellar deaths. The universe had to go through at least one generation of stellar birth and death before the chemistry of life became available. You required stars to die before you could exist. The second generation of stars enriched with those first heavy elements could form differently. The heavy elements allowed the gas clouds to cool more efficiently, to fragment into smaller pieces, to produce stars of a wider range of masses. Stars like our Sun. Stars that burn steadily for billions of years rather than millions. Stars patient enough to allow the long, slow chemistry of planetary evolution and biological complexity to unfold in their warmth. Around some of those second and third generation stars, the heavy elements did not all fall into the star. Some of them remained in the disk of gas and dust, surrounding the young stellar object, colliding and accreting and gradually building into planetesimals and then into planets. Rocky planets composed of the silicon and iron and oxygen and magnesium that dead stars had contributed to the interstellar medium over billions of years. Planets with surfaces and interiors in the right conditions, atmospheres. In the right conditions, that phrase carries more weight than it appears to. The right distance from the star for liquid water to be stable, the right planetary mass for gravity to retain an atmosphere without crushing it. The right atmospheric composition for the greenhouse effect to operate within a range compatible with liquid chemistry. The right magnetic field to deflect the worst of the stellar radiation. The right orbital stability to avoid the kinds of gravitational disruptions that would sterilize a surface repeatedly before life could gain a foothold. These conditions are not guaranteed. They are not the default outcome of planetary formation. They are the result of a specific combination of factors that must align across many scales simultaneously. And yet they have aligned at least once because you are here. The Earth is a world where the cold clouds made the star made the elements made the planet developed the oceans developed the chemistry developed the cells developed complexity, and the complexity eventually developed the capacity to look back at the cold clouds and the dead stars and the neutron star mergers and ask how all of it connects. That loop from cosmic extreme to conscious observer and back to cosmic extreme is perhaps the most remarkable thing in the observable universe. Not because consciousness is magic or because humans are cosmically special in the sense of being the universe's intended destination, but because the chain of physical events required to produce it is so long, so dependent on so many specific conditions, so contingent on the right things happening in the right order across billions of years, that its existence constitutes a kind of improbability that science has not yet fully accounted for, and perhaps never fully will. Now let us revisit the extremes we visited tonight through this lens. The cold of the Boomerang Nebula, that extraordinary 1 Kelvin colder than the space between galaxies, is the cold of a molecular cloud in an advanced state. It is the cold that precedes collapse. It is the cold that gravity will eventually convert to fire. Every cold cloud in the universe is a potential star, and every star is a potential source of the elements that planets and life require. The cold is not the absence of possibility. It is possibility in its most compressed and patient form. The heat of a supernova core, that 100 billion Kelvin that unmakes iron nuclei and rebuilds them into gold and platinum through the rapid neutron capture process, is the heat that stocked the periodic table beyond iron. Without it, the universe would contain only light elements. Without it, there would be no iron in your blood, no calcium in your bones, no iodine in your thyroid, no zinc in your enzymes. The violence of stellar death is the generosity of elemental distribution. The catastrophe is the gift. The density of a neutron star, that extraordinary compression of solar masses into city-sized volumes, is the density at which matter reveals its deepest nature. It is the laboratory where physics at its most fundamental is tested. It is also in the neutron star merger, the factory where the heaviest elements are made. The density is not merely extreme, it is productive. The compressed matter brought to conditions of maximum strangeness creates the elements that fill out the lower rows of the periodic table and end up in the circuits and jewelry and instruments of technological civilizations. The violence of the neutron star merger, the gamma-ray burst, the tidal disruption event, the violence that we spent so much of tonight attending to, is the violence of thresholds being crossed, of systems reaching the end of one state and being transformed into another. The violence is not gratuitous, it is transitional. It is the universe reorganizing itself at its most dramatic. The way of forest fire is not the end of the forest, but the clearing that allows the next forest to begin. And the emptiness of the voids, that profound billion light-year absence that we visited last, is the emptiness that defines the structure by contrast. The voids are what is left when gravity has done its work of concentration. They are the negative space in the cosmic web, the absence that gives the filaments their meaning, the dark background against which the luminous structure is visible. Without the voids, there would be no filaments. Without the low, there would be no high. Without the empty, there would be no full. Every extreme we visited tonight is part of the same system. The same universe expressing itself across scales, from the quantum to the cosmological, from the fraction of a second to the age of everything, from the temperature of 1 Kelvin to the temperature of the Planck epoch, from the density of a Planck epoch, void to the density of a neutron star core. And you are in the middle of it. Not at the extremes, not in the boomerang nebula or the supernova core or the neutron star interior or the cosmic void, but in the middle, in the narrow band of temperature and density and chemical complexity, where the universe's long investment in structure and process has produced something that can look back at the extremes and understand at least partially what they are. There is a perspective that sometimes arises when people first encounter the full scale of the universe. A perspective that says, if the universe is this large and this old and this extreme, then surely human beings are insignificant. Surely our lives, our concerns, our brief warmth on a small planet orbiting an average star in the outer arm of an unremarkable galaxy, surely all of that is rendered meaningless by the comparison. This perspective is understandable. It is even in a limited sense correct. We are small, we are brief, we are located in an ordinary part of the cosmic web far from any of the extremes we have visited tonight. But it makes a mistake. It confuses scale with significance. It assumes that because the universe is large, what happens in a small part of it cannot matter. And this assumption examined honestly does not hold. The universe spent 14 billion years producing the conditions for complexity. It went through the heat of the Big Bang, the synthesis of light elements, the formation of the first stars, the death of those stars in supernovae that distributed heavy elements, the formation of second and third generation stars with planetary systems, the long, slow chemistry of rocky planets with liquid water, the emergence of self-replicating molecules, the billions of years of biological evolution, the development of nervous systems and brains and language and mathematics and telescopes and gravitational wave detectors sensitive enough to feel the geometry of space-time shift when two neutron stars merge 130 million light-years away. All of that, every step of that 14 billion year chain, was required to produce a creature capable of understanding any of it, of measuring the temperature of the Boomerang Nebula, of detecting the gravitational waves of GW 170817, of building the instruments that observed a gamma ray burst 7.5 billion light-years away with the naked eye, of writing and reading and listening to a description of the full range of cosmic extremes at 2 a.m. while trying to fall asleep. The universe did not have to produce this. Nothing in the laws of physics required it. It is a consequence, not a purpose. But it is a consequence of extraordinary rarity and extraordinary depth, and it is worth recognizing for what it is. You are the universe examining itself, not metaphorically, literally. The atoms in your brain forged in stellar cores and scattered by supernova and gathered by gravity into a planet and organized by chemistry over billions of years into neurons are the universe's own material arranged into a configuration that can process information about the universe and form models of it and experience something that resembles understanding. That has happened at least once, here, now, in this moment, in whatever room or bed or quiet space you occupy. Whether it has happened elsewhere, whether the universe is full of minds examining it from countless locations, or whether this is an extraordinarily rare event, perhaps unique in the observable universe, we do not know. The answer to that question is one of the most important and most uncertain in all of science, but we know it has happened here. Now let us return one final time to the cold, because the journey began in the cold, and it is right that it should end there. Not in the Boomerang Nebula's extraordinary 1 Kelvin, not in the chill of molecular clouds where stars are waiting to be born, but in a different kind of cold, the cold of a quiet room, the warmth that is present in it, the warmth of a body at 37 degrees Celsius, 310 Kelvin, suspended between the absolute cold of the universe and the extreme heat of the stellar cores that made its material possible. 310 Kelvin. A temperature unremarkable by any cosmic standard, not the coldest anything has ever been, not remotely the hottest, not extreme in any direction, simply warm enough for chemistry, warm enough for thought, warm enough for the slow, stable, patient processes of biology that require neither the simplicity of absolute cold nor the destructive energy of extreme heat, but the narrow, comfortable middle where organic molecules can form and persist and organize, and eventually wonder about the extremes they are suspended between. You are at 310 Kelvin. The Boomerang Nebula is at 1 Kelvin, 5,000 light-years away, cooling as it expands, approaching the lower limit of thermal existence with patient inevitability. The core of the Sun is at 15 million Kelvin, 93 million miles away, fusing hydrogen into helium as it has been doing for 4.5 billion years. Sustaining the warmth that keeps the surface of this planet at a temperature where water is liquid and chemistry is possible and something can molter. Look up at the night sky and ask questions. The early universe was at 10 to the 32 Kelvin 14 billion years ago, in the first fraction of a second of time, producing the conditions that would eventually, after an extraordinary chain of events, produce you. All of those temperatures are part of the same story. The story of a universe that began in fire and expanded into cold and used the gradients between them, the flows of energy from hot places to cold places, to build every structure and process and complexity it contains, including the warmth in this room, including the warmth of a living body at 310 Kelvin, including the warmth of whatever you are feeling right now, whatever particular mixture of tiredness and curiosity, and the faint sense of having been somewhere very large and very strange and having returned safely. That warmth is not in spite of the universe's extremes, it is because of them. The cold made the stars made the heat made the elements made the planet made the conditions made the warmth, and the warmth, this particular arrangement of matter, at this particular temperature, in this particular moment, is capable of knowing all of that. That is not nothing. That is, in the full 14 billion year context of the universe's physical history, almost everything. Somewhere tonight, a molecular cloud at 10 Kelvin is beginning to collapse. In 1,000,000 years, it will be a star. In 5 billion years, that star may have a planet. In 10 billion years, that planet may have an ocean. In 14 billion years, something on that ocean's shore may look up at its night sky and begin to ask questions about the cold. Somewhere tonight, a neutron star binary is spiraling inward, Not in its final seconds, not yet, perhaps not for another 100 million years, but closer than yesterday. The gravitational waves it is already producing are spreading outward through spacetime at the speed of light, too faint to detect at any distance, carrying the news of an in-spiral that will one day culminate in a merger that forges gold and announces itself in ripples through the geometry of reality. Somewhere tonight, a massive star is in the last 10,000 years of its life, burning silicon in its core, building toward the iron that will end the engine, approaching the threshold. It does not know it is approaching in the outer arm of a galaxy 200 million light-years away. Somewhere tonight, at the center of a cosmic void, 400 million light-years across a single small galaxy, drifts in extraordinary isolation, surrounded in every direction by the most complete emptiness. The universe contains its stars, burning quietly, its planets turning the void around it, expressing the dominance of dark energy in the purest form available in the current universe. All of this is happening right now. All of it has been happening throughout this entire journey. None of it required your attention. None of it paused while you listened. The universe does not wait. It does not slow for consideration or speed for drama. It simply continues at every scale, in every extreme, in every quiet corner and violent intersection, in every cold cloud and hot core and dense remnant and empty void, all at once, all the time, with a patience and a consistency that makes the word eternal feel almost inadequate. And here, in the middle of all of it, in a room somewhere on a small rocky planet, orbiting a middle-aged star in the outer regions of a spiral galaxy, embedded in a supercluster that is itself one small node in the cosmic web, you are resting. The day has receded. The urgent things have stepped back. The body assembled from hydrogen made in the first 3 minutes of the universe, and carbon and oxygen and iron made in stellar cores that no longer exist, is horizontal or nearly so warm, breathing slowly its 100 trillion cells, carrying out their quiet chemistry at 310 Kelvin. You are in this moment the most complex arrangement of matter in the known universe, doing the simplest and most necessary thing, resting, allowing the chemistry of sleep to do what sleep does, consolidating, restoring, returning the body and the mind to the state from which tomorrow becomes possible. That is not a small thing. It is not a trivial thing. It is the thing that makes everything else sustainable. The cold rest between the hot days, the quiet between the events, the stillness that the system requires in order to continue. The universe has its own version of this, between the supernova and the next star, between the merger and the new chemistry, between the extreme and the possibility that the extreme creates. There is a pause, a period of expansion and cooling, a time when the material is spreading out, settling, waiting for gravity to begin its work again. The universe rests between its intensities. It always has, it always will. You are doing the same thing, at a very different scale, on a very different time scale, with very different stakes, but the principle is the same. Intensity requires rest. Extremes require recovery. The cold cloud needs to drift for millions of years before gravity is ready to make a star. The neutron star binary needs to orbit for 1 billion years before the merger is ready to happen. And you need this. Whatever this is, this quiet time, this dark room, this permission to stop, take it. The Boomerang Nebula is drifting at 1 Kelvin in the constellation Centaurus, 5,000 light-years away, colder than the space between galaxies, approaching but never reaching the absolute limit of thermal existence. A cloud of gas exhaled by a dying star, cooling as it expands, patient beyond any patience a human clock can measure. Somewhere in that cloud, atoms are barely moving. The motion that is temperature, the vibration that is heat, has been reduced to its minimum. Not to zero, never to zero, the quantum mechanical flaw sees to that, but close. Extraordinarily, beautifully close. And yet that cloud is not permanent stillness. It is temporary stillness. Gravity is patient. In millions of years the cloud will warm. In tens of millions of years it will collapse. In 100 million years, there may be a star where the cold now drifts, burning at millions of Kelvin, fusing hydrogen into helium, contributing its light to the galaxy, eventually dying and scattering its elements into new clouds, new cold, new possibilities. The cold is not the end. It is the pause before the next beginning. You are in your own pause before your own beginning. Whatever tomorrow holds, whatever the week brings, whatever is unresolved and waiting and uncertain it is on the other side of this quiet, it does not need to be solved tonight. It does not need to be carried through every hour of darkness. It can wait the way the cold cloud waits, the way the neutron star binary waits, the way the universe itself waits between its intensities. Let it wait. The warmth is here now, in this body, in this room, in this moment, made from the depths of stars, sustained by the light of a middle-aged sun, maintained by the patient chemistry of 14 billion years of cosmic evolution, working its way toward the extraordinary improbability of a creature warm enough to wonder and tired enough to rest. It is remarkable. It is temporary, and it is yours. Sleep well.